Hello, everyone. Today we will be talking about quantum teleportation. Let's start by talking about what it isn't. Well, it is not the situation where we have a qubit or any other quantum object in a box that we make disappear and reappear in another box. What it is the transfer of the state of a qubit to another qubit. You can think of it this way. We have a qubit in the pink box and another qubit in the blue box. The pink box qubit is initially in state ket psi in, while the one in the blue box is in ket 0, which is eventually made into ket psi in. In the process, the initial pink qubit is no longer in ket psi in. As we will eventually see, there's a third qubit that is needed as a helper in this task, depicted here by a qubit in a green box. For that, we will also consider the initial state ket 0. By the time the state of the blue qubit becomes ket psi in, the state of the pink qubit is no longer ket psi in, and the state of the green qubit is not in general ket 0. Here's the quantum circuit diagram for teleportation. We have 3 qubits, 1, 2, and 3, and we want to teleport the state of qubit 3 to qubit 1. The circuit is divided into 3 regions, A, B, and C. In the next few slides, we will focus on one at a time. Let's start with region A. Qubit 3, whose state is teleported, starts by being in ket psi in, while qubits 1 and 2 each start in ket 0. Ket psi in is any general 1-qubit state that can be represented by alpha ket 0 plus beta ket 1. In this part of the teleportation circuit, nothing is done to qubit 3, but maximal entanglement is created between qubits 1 and 2, and the final state of the 3 qubits together is given by this state. Now we move to region B. Before we delve into that, let me introduce you to the representation of measurements in quantum circuits. There are 2 of them here in the far right. Each is given by a box with a pointer, sort of like a current meter used by electricians. The line to the left of the box represents the qubit before measurement. The box itself represents the measurement, and the double lines on the right represent the outcome of the measurement, which is a classical bit of information, 0 or 1. Note that after measurement, one forgets about the qubit because on the practical level, it becomes hard to access it and control it. Now back to talking about region B. Remember the output state from region A shown here at the top left? That'll be our input state here. In this part of the circuit, we leave qubit 1 alone and perform operations on qubits 2 and 3 only. First, we apply a C0 gate on them, where qubit 3 is the control qubit and qubit 2 is the target qubit. The input state then transforms to this. Then, the Hadamard gate is applied on qubit 3, and with some algebraic manipulation, the total state of the system can be written this way. Notice that the way it's written implies that if we measure qubits 2 and 3, qubit 1 will be rendered into a state that has ket psi in embedded in it. If the measurement outcome of qubit 2 is A, where A is 0 or 1, and the measurement outcome of qubit 3 is B, where B is also 0 or 1, then this means that the projected state of qubit 1 is this. A and B are classical bits that can be classically communicated, for example, by a phone call or an email message to whoever is handling qubit 1. This information can be used in the next step to ensure that the state of qubit 1 is precisely ket psi in. We want to eliminate the operators x and z from that expression by using the relation x multiplied by itself is the identity, which is also what one obtains upon multiplying z by itself. In region C, using this property and the knowledge of A and B allows the application of the right combination of x and z operators, so qubit 1 ends up in ket psi in. Here's an exercise for you. This is the teleportation circuit we just studied together. If instead of ket 0, the input state For each of the two qubits, 1 and 2 is ket 1. How should the circuit be modified to teleport the state of qubit 3 to qubit 1? Hasta pronto!